looks physically like this. This is a chip that you might slide into a little slot inside of your computer, specifically on the so-called motherboard. Again, a big greenish board into which all of your computer's components connect. And there's usually a little divot here, a little bump to make sure you put it in the right way, this way, instead of, for instance, that way. And then on this green circuit board are all of these various chips that actually store your data. Specifically, they store your data in a volatile way, only when the power is on, when your laptop has battery and is running, or when your laptop is plugged in and is running. Which is to say, when you double-click an icon on the screen or run some program, open some file, those files are loaded into the little black chips that you see on this stick here. They're loaded into RAM, or random access memory. And this memory is pretty fast, and it is where those files and programs live so long as you are using them at a given moment in time. Now, other devices have slightly different looking sticks of RAM. This is a smaller stick here that's actually found typically in laptops or certain desktop models, but it's the same idea. It's simply a different form factor. Now, you can actually see in your Mac or PC sometimes exactly how much RAM you have, especially if you bought the computer without knowing this concept or were given the computer and didn't think to ask. In fact, on Windows, if you open up the so-called Task Manager and look at the CPU tab, you might see a little something like this. You'll see, a nice little chart that shows you what your CPU has been doing over the past few seconds. And the higher these peaks are, the busier it was. Maybe you double-clicked an icon or played a video or sent a really big email or something like that. But more interesting down here is the speed of your CPU. This one is 1.94 gigahertz. And a gigahertz means 1 billion things per second. So a CPU that's 1.94 gigahertz means that this CPU, this computer, can do 1.94 billion things per second. Additions, subtractions, multiplications, printing to the screen, any number of other things. But if we look, odds are this is marketed, frankly, as 2 gigahertz, and maybe it has burst technology whereby it can actually go even a little faster, maximum speed, 2.81 gigahertz, by maybe using a little more energy for some amount of time and therefore generating a bit more heat. But you'll see that there's only one socket in the computer from which I took this screenshot from Windows, which means there's one CPU, but that CPU has 2 cores, which means that the computer can do literally 2 things at once because it has really 2 brains inside of that device that we saw a picture of a moment ago. But logically, it actually seems to have 4. So this particular Windows computer has a CPU with 2 cores, each of which supports that technology called hyperthreading, which means that each of those cores will present itself to the Windows operating system as though it's 2, which is to say each core will do 2 things simultaneously, thereby giving me 4 logical processors, or really the ability to do 4 total things at once. So perhaps lower level detail than is perhaps germane, but these are the kinds of things that you end up paying for in a store when you buy a computer online. This is what distinguishes a less expensive computer from a more expensive computer, is just how fast the CPU or CPUs are, and just how many cores the CPU has, and therefore just how much work you can get done at a given moment in time, or just how quickly you can work more generally. Now, on a Mac, if you open up your system profiler, you'll see a different kind of interface, but similar information. This is taken here from a MacBook Pro. You can see that this CPU is 3.1 gigahertz, so faster, but it has 1 processor. Total number of cores is 2. And so here we see no mention of hyperthreading, which generally Windows is a bit more detailed on. But this does mean that this CPU is pretty darn fast, 3.1 billion things per second. And it actually has 2 cores, so it can do at least 2 things at once. All right, so that's my CPU, which does all of the thinking and all of the work. That's RAM, or random access memory, where all of my data and programs are stored while I am using them. So what else do I need? Well, where are those programs and files stored when the power is not on, when my battery is dead, or when my computer's not even plugged in? Now, odds are, if your computer is like mine, you don't lose all of your files and all of your programs just because your battery dies or you move a computer and therefore unplug it from the wall. That would not be a very useful device. Computers do have non-volatile memory that sticks around even when the power is lost, but it uses a different technology than RAM for that. It tends to use a disk or a hard disk, as in this case. So this is a device that a PC desktop or Mac desktop might have inside of it, and it actually stores quite a bit more information than a stick of RAM. A stick of RAM might store 1 gigabyte, 2 gigabytes, maybe even 16 gigabytes. But a hard drive, as this thing is called, will actually store 256 gigabytes, or maybe 1,000 gigabytes, aka a terabyte, or even 2 terabytes, or 4 terabytes, which is an order of magnitude more than our sticks of RAM. Inside of this device, though, meanwhile, is something that feels kind of old school. It's actually one or more metal platters that literally, physically spin around mechanically. And on those platters is your data actually stored. So in RAM, there were no moving parts. There is no fan. There's no motor. There's nothing to move back and forth. It's entirely electronic. It's all electrons at the end of the day. But a hard drive is a mechanical device that actually has one or more of these platters spinning and spinning and spinning. And that's what allows the computer to access different areas of those platters. And in fact, you'll see one or more of these little reading heads, not unlike old school phonograph or record players, that actually move back and forth and read the data from that device. And what's nice about this device is that it's non-volatile. It uses tiny, tiny magnetic particles, little specks of magnetic particles that if you orient them this way might represent a 1. If you orient them this way, it might represent a 0. So north to south pole, south to north pole, if you remember some of your electronics. But all that is to say is there's tiny, tiny, tiny little particles on here, billions or more perhaps, that depending on their orientation, up or down, represent a 1 or a 0. And if you have enough of those particles, you can represent bytes or megabytes or gigabytes or terabytes or more or anything in between. And so you have the ability to store data this way or this way, even when the power is off. The power is used just to read the data or to write or change the data. It doesn't need to stick around to persist the data. So in fact, why don't we take a look at what this motor looks like when actually running? This is a short video from the slow-mo guys, which gives us a sense of what the hard drive looks like when its lid is indeed removed like that there. Fascinating, I know. Well, now let's actually take the hood off of an actual hard drive, albeit via animation, and actually see and hear what it is that's going on. And in this depiction here, you'll see that the magnetic particles ultimately are represented as red-blue or blue-red particles, which represent precisely those magnetic particles that represent your zeros and ones.
The hard drive is where your PC stores most of its permanent data. To do that, the data travels from RAM along with software signals that tell the hard drive how to store that data. The hard drive circuits translate those signals into voltage fluctuations. These in turn control the hard drive's moving parts, some of the few moving parts left in the modern computer. Some of the signals control a motor which spins metal-coated platters. Your data is actually stored on these platters. Other signals move the read-write heads to read or write data on the platters. This machinery is so precise that a human hair couldn't even pass between the heads and spinning platters. Yet it all works at terrific speeds.
So where are those particles? Well, for that, we're going to have to zoom in even closer because they're not visible to the human eye.
Let's look at what we just saw in slow motion. When a brief pulse of electricity is sent to the read-write head, it flips on a tiny electromagnet for a fraction of a second. The magnet creates a field, which changes the polarity of a tiny, tiny portion of the metal particles which coat each platter's surface. A patterned series of these tiny charged-up areas on the disk represents a single bit of data in the binary number system used by computers. Now, if the current is sent one way through the read-write head, the area is polarized in one direction. If the current is sent in the opposite direction, the polarization is reversed. How do you get data off the hard disk? Just reverse the process. So it's the particles on the disk that get the current in the read-write head moving. Put together millions of these magnetized segments and you've got a file. Now, the pieces of a single file may be scattered all over a drive's platters, kind of like the mess of papers on your desk. So a special extra file keeps track of where everything is. Don't you wish you had something like that?
Now, anytime you have a physical device like this that's spinning all day long or for months on end, if you use your computer a lot and for quite a long period of time, something could go wrong. Maybe you accidentally bump the desktop or the laptop, the result of which is that this reading head might actually strike the platter and make a dent in it or some kind of scratch, which actually will corrupt not only some of the data perhaps, but might even stop the whole device from working if the reading head no longer functions properly. Moreover, anything that's physical like this isn't going to spin all that fast at the end of the day. Now, technically, a hard drive like this might spin 7,200 times per minute or even 10,000 times per minute, but that's much, much slower than the speed at which electrons travel as they would in something like RAM. Well, fortunately, it turns out that there's something in between those technologies that doesn't have moving parts, but that's not quite as fast as RAM, but that is non-volatile, whereby it will store your data persistently even when the power is off. And this is so-called flash memory, or a solid-state disk, SSD, in this case here. It's a smaller device, whereas typical hard drives that have moving parts are very often 3.5 inches, though 2.5-inch versions do exist as well in diameter. A solid-state drive tends to be only 2.5 inches in width, so that it actually fits inside of computers in the same slots that older, more mechanical hard drives might fit, but it doesn't have moving parts. In fact, if we open it up, you'll see something very reminiscent of the RAM we saw earlier, but the technology inside of this device is such that the data persists, even when your battery dies or you unplug your laptop or desktop. But the upside of an SSD being entirely electronic is that it's much faster. And so this means that your programs will load faster when you double-click them. Your files will open up faster when you double-click on them. And anything you might do or save to your hard drive, or solid-state drive in this case, will actually get saved much more quickly, which means you might see a little hourglass or a spinning beach ball much less frequently, and your computer is going to behave and certainly feel faster. Now, the catch is that solid-state drives theoretically won't necessarily last as long, depending on the quality of the brand and the technology being used, whereby they only have a finite number of writes. You can read from them nearly as much as you want, but over time, they'll degrade in terms of how many times you can keep writing to them. Now, for many people, this might be a non-issue, but to mitigate against this, has the industry also introduced what are called hybrid drives, hard drives that might be the same size as this or the same size as a 3.5-inch drive, like the spinning mechanical device we saw a moment ago in our animated form, but they might have both some solid state memory and some mechanical hard drive memory, so that you might have a few megabytes or gigabytes of solid state memory, and you might have a few gigabytes or terabytes of traditional hard disk space. And the device itself moves your data around in a clever way so that it tries to keep as much of the data that you want to use at a given moment on the solid state part of the device, so that it's readily accessible for you. And the data that you might not need right then and there stays on the slower, more mechanical device, where nonetheless you have a lot more storage. Now, flash memory is something you might have heard about before now, but in the form of these things here, USB sticks that might store a gigabyte or 16 gigabytes or more, but it's data that you might want to carry around on your keychain or in your pocket or keep around on your desk simply for transferring files from one computer to another or keeping some data with you. They tend to be slower, though, than solid-state drives. They tend to be less reliable, but they also tend to be much less expensive, but also smaller in capacity. But the technology is very similar in spirit. If you need more storage space than that, you might actually carry around with you a solid-state drive externally. So it might be a little bigger and a little heavier, and not something you want to put on your keychain, but this might store 256 gigabytes of space, or even a terabyte of space, all of which is now carried around externally. And via some kind of cable, can you plug this device into your laptop or desktop, or maybe a friend or a colleague's computer, so that you can share files without having a local network. If you need even more storage than that, a terabyte, 2 terabytes, 4 terabytes or more, you might actually have another type of external hard drive, inside of which is one of those older, more traditional mechanical drives, the 3.5-inch disk devices that might store much, much, much more data. But the price you pay is that it's a mechanical device. It might be, therefore, a little bit slower. And so ultimately, there's this trade-off between how much space you get, how much money you're spending, and how quickly you can get data from and to that external device. In fact, there's this whole series of trade-offs that we've seen thus far. And you can actually think of these various types of memory inside of a computer like a funnel of sorts, whereby you have a pretty big opening where you keep a lot of your data. on the biggest of your devices, but the goal is to get that data closer and closer and closer to your computer's brain, where it can do some actual work. And indeed, if you think of the CPU as being at the bottom of this funnel, that's to whom you want to get all of this data. So throughout this funnel, you might have your hard disk or your solid state disk up here, which stores a lot of your files, a lot of your programs persistently in a non-volatile way so that it's permanent even when the power or battery no longer works. But that hard disk or solid state disk ultimately feeds information down to your computer's RAM. But the RAM is not the last stop before the computer CPU. It turns out that there's other types of memory that a computer has that you might even see mentioned on your computer screen. So if up here you have your disk, whether it's a hard disk drive or a solid state disk drive, you might have quite a bit of this. This might be in the